Welcome to Brain Vision.
So I've provided an illustration of the situation in this case. So we have particles that are incident from the left. And so we're going to have to divide our problem up into two regions. So in region 1, there will not be a potential, but there will be in region 2. This means that we're going to have two forms of the wave function. So region 1, the wave function will have two terms. And that means a transmitted, well, region 1 will have an incident, I should say, incident wave function. That's this first term that you see right here. And the second term will be a reflected term. And in region 2, you'll simply have a transmitted term. So this corresponds to particles that actually make it through the potential, or make it through and are transmitted despite the fact that there is a non-zero potential. So if we have a reflection probability, then we have to think in terms of B and A, the coefficients B and A, because after all, this term right here corresponds to reflected particles, because you see this minus sign right here, e to the negative I k1x. That means the particles move to the left. They move in the opposite direction as the incident particles, e to the I k1x, which move to the right, which are incident. So we would, of course, have our reflection coefficient defined in terms of the ratio B over A. So that reflection coefficient will be determined in this problem. And it'll actually be the square of that ratio, B over A. So what we have to do to get to that point is look at the boundary condition at x equals 0. There's actually two such conditions. The condition that at x equals 0, the wave functions psi1 and psi2 are equal, and that their derivatives are equal to each other. So d psi1 of dx and d psi2 dx are equal to each other. So we're going to evaluate those equalities in this problem, and we're going to arrive at r equal to b squared over a squared in terms of wave vectors, which are defined as well. And before we get there, though, we need to go ahead and evaluate the wave vectors in terms of the energies. So we look at the Schrödinger equation in regions 1 and 2. So we'll start with region 1 and get the wave vector in terms of energy E1. This way, when we're given numerical values for the energies, we can get values for the k vectors ultimately. So we go ahead, we substitute in the wave function for region 1 into the Schrödinger equation, knowing that the potential is 0 in this region. And we proceed as follows. We take the derivative twice, which is what the second derivative does, and we go ahead and we get a relation from this. So we get negative k1 squared on the terms of the wave function on the left-hand side of the equation. And now we factor k1 squared out. The minus signs go away on the left side because we had negative h bar squared over 2m times negative k1 squared. And so we have h bar squared k1 squared over 2m multiplying the wave function on the left, and we have E1 multiplying the wave function on the right. So we get the energy E1 equaling h bar squared k1 squared over 2m. And so we'll go ahead, scroll down a bit, and you can see that relation, and you can see how these two constants multiply the wave function on both sides. And so proceeding as follows, we go ahead and we get the wave vector k in terms of the energy. Now we look at region 2, where there is a potential u, and we do a similar calculation. And so I'll kind of go a bit faster through this because you see that it's the same method. So you would just go ahead, you substitute in your wave function, you take a second derivative. This time, though, you do have a potential term. And to deal with the potential term, since our potential is a constant, we don't have to worry about it being a function. you would simply subtract it over to e. And we'll go ahead and move down right here. And, as you take the second derivative, you can go ahead and move u over to the right-hand side by subtraction, and you'd have e minus u, which is another constant. Instead of e, you just have e minus u. It's really e2, but we can go ahead and label that as e2. And now you have, once you get h bar squared k squared, or k2 squared over 2m, you'll have e2 minus u, and then you can take a square root, and you get that k2 is equal to the square root of 2m minus e2 minus u over h bar. So now we look at our boundary condition at x equals 0. And I say boundary condition because it literally is the boundary at x equals 0 between the two regions. So psi 1 equals psi 2. At b equal, this means that at this point, a plus b is equal to c at the boundary. And we also have the other condition that the derivatives have to be equal. And when you take their derivatives, only the first derivatives, and you set x equal to 0, you obtain the condition that ik1 times a minus b is equal to ik2 times c. So that's simply from only taking a first derivative. You don't have to worry about the second derivative. If we had taken a third derivative, you would have three conditions. You would then have that the functions are equal, the first derivatives are equal, and the second derivatives are equal. But in this case, because we have a second order differential equation, you only have to worry about the wave functions equaling and their first derivatives equaling. If we had a first order differential equation, you would only have that the wave functions are equal, and you wouldn't worry about their derivatives equaling. So that's how that works. You'll know how many boundary conditions you have based on the order of the differential equation. So if you have a second order, then you have two conditions, as we have here. So continuing on, we can rewrite our conditions as follows. We can take the a minus b condition, which is our second condition, and we can divide both sides by ik1. So if I just go ahead and quickly divide this by ik1 on both sides, the i's go away, and on the left side, everything goes away as far as ik1 are concerned, and I'm left with k2 over k1 on the right side, multiplying c. And so I have a minus b equals k2 over k1 times c, and I still have my other condition that a plus b equals c. And there's a reason for doing it this way, because we can add these together. If I add them together, I get an equation for a, basically. If I were to subtract them, as we will in a little bit, we'll get an equation for b. And by having equations for a and b, we'll be able to get r. So there's a motivation for doing all this math, basically. So when I get to a through addition, I get that k2 over k1c plus c, which can be factored, equals k2 over k1 plus 1 times c. Now, if I subtract the following way, you have to be specific in how you subtract because order matters with subtraction. Then if I do it this way, if I say a plus b minus a minus b, then I get c minus k2 over k1c equals 1 minus k2 over k1c. But that is actually equal to 2b. So now, if we remember the definition for r, it was b squared over a squared, which is actually equal to 2b over 2a, and then you square that because the 2's will go away. I mean, notice here, of course, that the 2's go away, so you have b squared over a squared. We can then substitute what we have for 2b and 2a. So we have 1 minus k2 over k1 squared over 1 plus k2 over k1 squared. And we can rewrite that. If we put this k1 as, a denominator, as a common denominator with the 1 here, and this K1 is a common denominator with the one here, then we're going to have the following expression for R. We're going to have K1 minus K2 over K1 plus K2. You just do a little algebra with common denominators, and you end up with K1 minus K2 over K1 plus K2 squared, which is the result that we want. And that's what you get. If the K vectors were the same, in other words, there were no difference in potential energy between the two regions, then the reflection coefficient would be 0, and then you would have complete transmission. Now, if we keep going, knowing that we have an energy of 7 electron volts and a potential of 5 electron volts, we don't even need to know the mass of the particle, because we can do some factoring and we can get the reflection coefficient in terms of just the energies. Because this is the whole reason why we got the K vectors in terms of energies earlier. It was kind of lengthy, but we did it for a reason. Because now, substituting in these expressions of K vectors in terms of energies, we put them into our expression for reflection coefficient, K1 minus K2 over K1 plus K2, and we square that, and this is what we do. Now, we just write it out like this. And notice that the square root of 2m over h bar cancels out completely. And now we're left simply with energies. And we know the energies. And remember to square. And now you'll get simple expression with square roots. So now you put in your square roots, and you get a reflection coefficient, which, is a probability. So you can write it as a percentage, 9.2% probability of reflection. Now, if you subtract 0.092 from 1, you'll get the transmission coefficient, which is 90.8. So because our energy is greater than our potential, you're most likely to be transmitted. The particle is most likely to be transmitted, and that'll happen 90.8% of the time.